we have a very important lesson to discuss because we are now going to introduce the concept of rotational inertia. So just like we had mass was inertia for linear motion, we are going to have moment of inertia equals I equals rotational inertia. We're going to manipulate some familiar equations and come up with an understanding of what rotational inertia is. We're going to do this by considering, as it says here, a wheel made up of many point particles, little m, and we're going to calculate the torque on one of them from some general force. So we're just going to let a general force F pull on one of the point particles that makes up the mass. We have the pivot is the center of the wheel, so there's our pivot point. Our vector r in our cross product, r cross F, goes from the pivot to where the force acts. We come over here, we draw them from a common origin. We are going to right hand rule, so perpendicular right hand, kind of a karate chop, index finger pointing straight up, make a fist, thumb out of the paper. So it's a positive torque, a counterclockwise rotation. When we curl r cross F, in this case we are going to let r cross F do all the mathematical work for us, and we are going to want it to calculate the F tan, the F sine theta. So that's why I have the F tan, F sine theta here that we want to address. And I just want to put a green arrow here because we're going to track the R in R cross F in our analysis on this page as well. Well, since F sine theta equals F tan, well, we know from Newton's second law, F tan equals ma, where A would be A tangential. Since the point particle we're looking at on this wheel is also rotating in a circle, we can replace A tan with alpha r. So we do that. We replace the A tan with alpha r as it's shown here. So we get F tan equals m alpha r, and we substitute that back in to our bracketed term here, so that our torque equation, so I hope you're following this, and that's why I had the green R. I'm tracking this green R is that green R. The F tan becomes m alpha r. We have two R's, mr squared alpha, and look at what we have. Now we have the structure we're looking for. We have torque equals mr squared, and we're going to bracket that together. That's going to become our rotational inertia term, times alpha. We have torque is the cause, causing the rotational acceleration. Mr squared is our rotational inertia, and the effect that we see is our rotational acceleration alpha. Kind of cool. And just to remind us of what we did linearly, F equals ma. F was the cause of the acceleration. Acceleration is the effect that we see. And we understood mass as the inertia property, that resistance to change in motion. The bigger the mass, the harder it is to speed it up, the harder it is to slow it down. And it's the same for rotational inertia. The bigger the mr squared, the harder it is to get it to start rotating. The bigger the mr squared, the harder it is to stop it from rotating. Well, if we calculated the mr squareds for all of the pieces that make up the wheel, right, that would be a computational way to get an estimate for the moment of inertia, and calculus will help us get an exact calculation for the moments of inertia. So for right now, we have an expression to calculate the moment of inertia for any point particle, mr squared. So any point particle that's part of a rotating system, the moment of inertia for that point particle is mr squared. And that's what I have here. So we will have other expressions for the moment of inertia of bigger objects like spheres and bars and other objects that have mass distributed in different ways. And calculus will help us make those the determination for those equations. But it is important, and again, whatever you do, whether you highlight or whether you do these explosion blasts that I have, This is the equation we use for point particle systems. And if we're going to peek ahead real quick, part of this lesson will be to do a point particle system, which I'll get to in a moment. Well, Newton's second law for rotation then becomes torque equals I alpha. It's that cause and effect relationship we just talked about. So I'm going to leave it to you to read what I have here about how to think about torque. I just have a few notations that are super important. You always have to start with your pivot point, and what is also super important is that equilibrium now means for us that the sum of the forces have to equal 0 and the sum of the torques have to equal 0. If both are not true, then we cannot say that an object is in equilibrium. Now we have two types of equilibrium. We have static equilibrium, where sum of the forces equals 0 and sum of the torques equals 0. Means you have an object that is not translating, right? Sum of the forces equals 0. No translation, meaning no x movement, no y movement. Sum of the torques equals 0 means you have no rotation, right? So static equilibrium means basically you have nothing. It's a static problem. Dynamic equilibrium is when you're moving with constant velocity, whether it's the linear velocity or the rotational. And in general, we certainly can have both happening together. So if you take a wheel, like the wheels on the bus, go round and round. Well, the center of mass of the wheel is going forward. There's your V. The wheel is going round and round. So there's your omega. You definitely can have both at the same time. And from now on, we're going to have both at the same time. The last part of this lesson is for you to get some practice with point particle systems, and as we peeked ahead, here you have a point particle system torque example. So I want you to think of this as kind of like a pinwheel. So those dashed lines connected down here to the pivot point, so those bold dashed lines represent kind of the bars of the pinwheel. The arms of the pinwheel, so they are, for us, going to be negligible mass. So these, I'm going to put them in as light blue for right now. Those light blue, you don't have to put in light blue, but so these blue that I'm putting in, those are the light rods of the pinwheel, and the pinwheel has these masses. You are going to follow exactly what it says. You are going to take the values for mass 1, mass 2, mass 3, and you're going to calculate moment of inertia. mr squared for mass 1, mr squared for mass 2, mr squared for mass 3, and get the total inertia of this pinwheel system. You are then going to calculate the individual torques, R cross F. You're going to calculate the angular acceleration because torque equals I alpha. We now know the torque, we know I, we should be able to get torque equals I alpha. Once we have alpha, we can use our constant acceleration equations, hopefully, to calculate the last part of this question. So I'm going to let you pause the video here, work on this problem. You can then unpause and we'll take a look at the answer. So pause the video. Okay, hopefully you've unpaused, and I will leave this here. You can pause the video again if you wish to take a look at the solutions. We are going to go over this in class, so I don't want to take more of our video time to go through the solution in detail with you, but please make any notations for anything that is in the solution that does not look correct to you or you have questions on it all, and we will do this again in class together. Very important lesson. So go back and watch what you need to watch because we will be using this again and again.